We're going to continue on here, chapter 7, going backwards. And we're going to talk about thermodynamics a little bit here, more about energy, which they really should do first semester, but they don't here. And then we'll go back and pick up the rest of thermodynamics. So we're going to talk about in this chapter, as it mentions there, energy. So let's get into that. So when we talk about thermodynamics, one of the main things that we look at when we're dealing with thermodynamics is the idea of a system and really its surroundings. So your system in a lot of cases is like your test tube, your beaker, whatever you may be doing the experiment in. And the rest of everything else is basically the surroundings. And in this particular case, we're going to talk about really energy and the flow of energy or heat from the system to the surroundings, or really even the surroundings back to the system. So we're going to have this sort of flow of energy occurring really in both directions. Now, when we talk about systems, there's really three types of systems that we deal with. We have an open system, and an open system pretty much can exchange energy and mass with the surroundings. So that would be like an open beaker. Just kind of take stuff out and put stuff in, and also can exchange energy with the surroundings. A closed system will transfer energy, but not mass. So you put like a stopper on your flask, then you can't take stuff out and you still have that energy flow. And we also have an isolated system where there's really no transfer of mass or energy in it. And in this case here, again, open system, we could take stuff in and out. We also have that flow of heat and energy in and out. Put a stopper or something on there. Again, going to stop that sort of exchange of mass, but could still do that. In an isolated system, again, pretty much everybody's just inside, really no exchange of anything basically occurring. Now, when we talk about energy, energy is really the capacity to do work or to produce some type of change. And energy can be measured as the work done or the force times the distance. There's different types of energy. There's chemical energy. That's the energy, for example, there's energy stored within bonds, within atoms. So, for example, if you were to break a bond, that would be a endothermic process. You have to put heat and energy in to do so. Everybody gains some energy and they kind of wiggle away from each other and the bond breaks. If you want to actually make a bond, that also requires actually energy to be released in that case, which is exothermic, because everybody has a lot of energy. When they release the energy, they slow down and allows them basically to come together to make that bond, as opposed to when you already have a bond, you add energy to it and they wiggle away from each other and they're able to basically break away from one another. There is potential energy, which is the energy due to the position. The classic potential energy example, the big giant boulder on the tip of the hill there that's going to fall. It has a certain amount of energy due to its position. It could then perhaps come over the hill and convert into some kinetic energy, right? As we come down the hill, that's the energy of motion. Then it's going to flatten whoever's underneath there. Hopefully nobody's underneath there. It will also transfer some energy to whoever was underneath there, and also the cement ground there as well. So the law of conservation of energy is that energy can neither be created nor destroyed, but it can be transformed from one form to the next. Again, in this case of our example here, certain amount of potential energy transformed to kinetic energy. And again, as it hits, it's going to transfer some of that energy, obviously, to whatever is underneath it. And we think of energy as sort of this nice, perfect transfer of energy. So the idea here is if somebody loses a certain amount of energy, somebody else should gain the exact same amount of energy. So, for example, if a reaction gives off 5 kilojoules of energy, the surrounding air should pick up that 5 kilojoules of energy. So this nice sort of perfect sort of transfer of energy that sort of happens. Now, thermodynamics, like energy that we're looking at in really this chapter, and we'll cover the rest of sort of thermodynamics in the next chapter. But thermodynamics is really the study, in this case, of the interconversion of heat and other kinds of energy. And a lot of what we look at is in the next chapter in terms of thermodynamics. Thank you. We look at the idea of whether or not a reaction will take place. And a lot of that is sometimes dependent on energy and energy being sort of dispersed from one state to the next. Now, there's a lot of properties that are determined really by the state alone. And that is basically what I refer to as state functions. State functions does not matter really the path you take to get there. There's kind of only two things that are really important when you're talking about a state function, and that is kind of where you start and where you finish, basically. So if we look at these two hikers, for example, here, hiker in the red here took the scenic route around the mountain, took some pictures, some selfies as he was coming up the mountain. The blue guy here took the more direct route up the mountain. In terms of their potential energy, they basically have the same potential energy as they both started and ended in the same sort of spots, basically. And things like energy, pressure, volume, temperature, those are all state functions. Really, the only two important things is where you start and where you finish. And that's why a lot of times we take, for example, our final minus our initial in terms of like volume and energy and pressure along the way. Now, when we're talking about reactions, as we'll talk about, right, when we talk about a reaction where we have reactants that go to products, our final state is pretty much our products, right? Our initial state there is our reactants. So a lot of ways that we calculate thermodynamic sort of properties is to take products minus reactants, which gives us basically where we ended versus where we started in terms of like energy and so forth. So if you end in energy, higher than where you started in terms of your reactants, you may have like an endothermic process where you actually absorbed energy overall. Vice versa, if you ended lower in energy of your products than where your reactant started, then you'd have more like an exothermic reaction where energy was sort of released. Any questions on that there? So when we talk about energy, there are several types of units that are commonly we come across here. There's a bunch of them. None of these are negative, by the way. That's just from PowerPoint. So scratch all that out there. So the SI unit there, SI, throwback name. The SI unit there is a Newton meter, which we never use here, but we use a kilogram meter squared second squared. And more commonly, units of energy are joules and kilojoules are very common units of energy, along with calories and kilocalories as well. These are two very common sort of units of energy. This relationship does pop up, and maybe you saw it probably last semester. 1 joule is equal to 1 kilogram meter squared second squared. So that is a conversion that sometimes does pop up. There obviously is 1,000 joules in a kilojoule. A calorie, which in this case is a lowercase c calorie, is basically the amount of energy required to raise 1 gram of water by 1 degree Celsius. So that's sort of a definition of a calorie. And an important sort of conversion between calories and joules is this one, which is 4.184 joules is equal to a calorie. That is also, as we will see, and maybe you remember from, since they don't teach it last semester, we'll have 100. That is also the specific heat of liquid water, 4.184 joules per gram per degree Celsius. One way that we use energy is to change the temperature of a substance. Again, ice to liquid water obviously requires some energy being inputted to do that. The ice cube needs to pick up energy, and that's also, as we'll talk about in a later chapter, it's also a spontaneous process, right? If you take an ice cube out, it'll just start melting by itself, right? And it'll pick up all that heat and energy from the surrounding air, and it will start to the melting process at that point. Some other sort of units of energy. There's also, in terms of calories, there's also a capital calorie with a capital C. That is sometimes referred to as a nutritional calorie, and that is equal to 1,000 of the little c calories, and that also equals 1 kilocalorie. So a capital C is more of a nutritional calorie, like calories you ate, calories you exercised off, all those type of things. And that is 1,000 of the little c. So there is a difference if you capitalize C per calorie versus non-capitalization of the C. And again, in most cases, we deal with usually the smaller c, unless you're doing something with nutrition as well. Now, thermal energy is the energy associated with the random motion of atoms and molecules. And thermal energy is based on really how many particles, atoms, molecules you got there. The more atoms, molecules, and stuff in the substance, the more thermal energy you're going to have, because there's going to be a lot more people moving around, vibrating and bouncing around and motion and all that kind of stuff. And that's going to cause a lot more thermal energy. Again, thermal energy is different than temperature. Temperature is sort of a measure of the energy change that occurs within a substance. And to sort of illustrate the distinction between thermal energy and temperature, if we took, for example, a cup of coffee that is at 70 degrees Celsius, and we took a bathtub here of water that's at 40 degrees Celsius. The bathtub of water has a lot more thermal energy than the cup of coffee there, even though the cup of coffee has a higher temperature as well. And again, that's because the bathtub there obviously has a lot more water molecules in it than your cup of coffee, I hope. Otherwise, you're drinking too big of a cup of coffee. But the temperature difference is also a difference that you see there. The reason for that has something to do with what we'll talk about in this class as well, in this chapter, the specific heat capacity, for example, of liquid water. There's a lot less liquid water there in the coffee cup, which means you don't have to put as much energy in there to see a bigger degree difference in terms of the temperature. You would have to heat that bathtub up a lot there to put a lot of energy in there to get it up to 70 degrees. It's kind of like when you boil water to make pasta, you put water in the big pot. It takes a while for it to boil, right? Put a small little pot of water up there with not a lot of water in there, it's going to start to boil a lot quicker, right? So it takes a lot more energy input to change the temperature of a big amount of water than it does, say, a small amount of water to do so. That's why people get worried about the ocean, right? When it goes up just a small amount of temperature degree, right? Think about how much water is in the ocean. Just to move it that much of a temperature degree takes a lot of energy to do so, as the specific heat of water is pretty high. Any questions on that there? So when we talk about heat, heat is defined as the flow of energy due to a temperature difference. Heat always flows from the hotter object to the colder object, and that is always a transfer of heat. And when we have a process that is exothermic, that is when heat and energy is released from, for example, the system to the surroundings. And that is sort of a release of energy, which is exothermic. If we lit a match, if we lit a Bunsen burner, you could put your hands carefully near the fire there, and you can feel the heat coming off of it, right? Being released to the surroundings. In an endothermic process, heat and energy is being absorbed by the system. And that, for example, is like our ice cube, right? We take our ice cube, as we just talked about, you take it out, it picks up all that heat and energy, because at that moment, the ice cube is a lower temperature than the surrounding air, right? Which is a higher temperature. And that's going to mean the air is going to transfer its heat to the colder ice cube and going to cause it to start to melt. That's also why when you make ice cubes and you put water in a tray like you used to do years ago and put those into the freezer to freeze it to make ice cubes, That is when you put your room temperature water into the freezer. The freezer's temperature is colder than the room temperature water, so the water loses all its energy to the surrounding temperature, and that freezes your water right into your ice cubes in that case. So again, heat always flows from hot to cold. Endothermic and exothermic processes are a lot of what we deal with in terms of really the first law of thermodynamics, which is all about really energy. These are some energy diagrams, and they represent both a exothermic reaction and an endothermic reaction. And when we look at these energy diagrams, there's some important parts. First off, here we have our reactants going to our products here. And the first thing that we see is we basically have a difference in energy of our reactants to our products. And if you take that difference in energy from where the products end to where the reactants start, this is what is referred to as we'll talk about a little bit later on here in this chapter, the delta H of this reaction, which is the change in enthalpy. That is a fancy way of saying how much energy is either gained or released in a chemical reaction, basically, is the delta H value. The way that we calculate, for example, the delta H, or one of the ways you could calculate the delta H of a reaction, is you take the delta H of your products, again, your final state, minus the delta H of your reactants, which is your initial state. And if we look at this situation here, my products are lower in energy than my reactants, which are higher in energy. So that's a lower number minus I guess we'll go with a larger number. So that would be more of a small number, I guess is the way to do that. Small minus a large number, right, will get you a negative value. So if you have a delta H that is negative, that is going to tell you it's a exothermic reaction because your products overall in energy actually ended up lower in energy than where the reactant started. The only way that happens is you have to give off energy in that reaction. And that is your definition of an exothermic reaction. Now, that is different than what we see over here in an endothermic reaction. This is our reactants over here. This is our products over here. And the difference between the reactants, again, if I could draw a straight line, and the products here is going to be our delta H of this reaction. And when we think about what's going on in this one, our products, which is our final state, is actually a larger value than our reactants, which is a smaller value or a lower value of energy. That's going to yield you a positive value for the delta H in an endothermic reaction. You could also think about the only way the reactants can get up there in terms of energy needs to go in or be absorbed basically as a result of this reaction. That is probably the most common way in chemistry that you know whether or not the reaction is exothermic or endothermic. It is based again on that sign that happens. So what happens in a chemical reaction, as you hopefully know, the only thing that happens is bonds break and we make new ones, right? So we break all the bonds of our reactants and then they reform new bonds on the other side to make our products. And that is actually happening as it goes from reactants to products here, as it's going up this hill, as it is climbing this hill to get to the very top. This hill from the reactants to the very peak of the hill, this is what is known as the activation energy, or the E of A. That is the activation energy. It is the minimum amount of energy that's required for a reaction to take place. And if we look over here on our endothermic reaction, this right here is our activation energy to the top of this hill right here. is our E of A as well. When we get to the very top of the hill of this sort of energy curve, we are pretty much at the highest point in energy, which would be right about there and right about there. This sort of highest point of energy is what is referred to as the transition state. And that would also be obviously a transition state right there. And that's the highest point of energy in terms of this reaction that's occurring. One thing that we hopefully know is, are things in chemistry more stable or less stable if they're high in energy? Less stable, right? The whole point of pretty much everything is to get everybody kind of in the lowest energy possible. So this is really your highest point along the way in a chemical reaction. It's the highest in energy. And what happens is you actually have something up here, which is sometimes has like a little symbol like that, like a transition state sort of symbol. This guy at the very top of the hill is what is referred to as the transition state complex, or sometimes referred to as an activated complex. And basically what that thing is really your transition between reactants and products. So as these reactants are climbing up this hill, what is starting to happen is all the reactants are starting to break their bonds. So they're partially starting to break away their bonds. At the same time, they're actually starting to make their new bonds. So it's this really sort of, I'm partially breaking some of my old bonds, and I'm also starting to make some of my new bonds along the way. And when we get to the very, very top, that is why we get this transition state complex. We got a guy that basically has partially made bonds and also some partially broken bonds, which is why it is also very, very unstable. It doesn't hang around for a very, very long time. A lot of reactions, it's very hard to, for example, try to isolate that guy in the middle point there because it's so high in energy, it's so unstable. It doesn't hang around a very long time. And what typically happens is it will kind of drop down the hill relatively quickly to get to the other side. At that point, again, we have that sort of exchange in energy, which either results in an endothermic process or an exothermic process. Any questions on that there? Yeah.
Yeah, I know. What at the transition state, like what is the downslope?
Yeah, so this is more for a chemical reaction, what we're looking at here, right? That's more of a physical change, right? The melting of the ice and stuff like that. What happens sort of in between those two is actually you have a little bit of both actually happening. It's kind of like what happens at the transition state where we got partially made bonds, partially broken bonds. Where that happens is like at 0 degrees Celsius, for example. At 0 degrees Celsius, you got like liquid water and also ice at the same time, like ice crystals. So you got a little bit of everybody in equilibrium with each other sort of occurring at that point. So it's kind of similar to what happens in chemical reactions where you got at that kind of height of energy where it's going to kind of come to the products. You got like partially broken bonds, partially made bonds, you got everybody kind of together at that point. Now, when we do have a chemical reaction, there is one way that we can sometimes speed up a chemical reaction, as you may remember. So we got a little go this way, our reactants and our products, right? And this is our activation energy, right? Now we could add a catalyst, right? And a catalyst is not a reactant. It is not a product. And it does not get used up in the reaction. Really, the point of most of the time when you add a catalyst is to speed up the chemical reaction. It does that by finding a more efficient pathway for that reaction to take place. And ultimately, by finding that sort of more efficient pathway for that reaction to take place, what happens in terms of our diagram here is in a catalyzed reaction, we typically are able to lower the activation energy by finding that more efficient pathway of doing so. What that essentially does is, right, the idea here of the activation energy is it's the energy barrier to allow a reaction to take place. And there's only a certain amount of reactants that have sufficient amount of energy to get up and over the hill to the other side. So when you add a catalyst, what you're doing is lowering the hill. That's going to allow a greater proportion of reactants to get to the other side, and thus usually increases your rate of reaction. Like if you had to walk a giant hill to get to the other side of campus, or just had to go over like a speed bump, right? A lot of people can get up and over the speed bump, right? A lot more people. And then maybe if they had to walk a giant hill to get to the other side. And that's the idea here of a catalyst and why it's able to sort of speed up the reaction. Also why, typically speaking, if you remember from kinetics, when you raise the temperature of a reaction by like 10 degrees Celsius, it usually will double the rate of the reaction for a lot of reactions. And because when you add more energy to your reaction or increase the temperature, your reactants now gain more energy, and there's a greater amount of reactants that have enough energy now to get up and over the hill, which is why your reaction would occur faster. Or if you put everybody on ice, you're going to see your reaction probably slow down because now you have less amount of reactants that have enough energy to get up and over to the other side. Maybe you did that in that last kinetics experiment, 200 a day. There was like a hot water bath and an ice bath versus the room temperature and how long it took to turn purple, blue, purple. One of those, blue or purple, I think. I don't remember. Because it's usually at the end of the semester and go, why are we doing this experiment? All right, so here's some other sort of energy diagrams, but again, here the formation of liquid water from hydrogen gas and oxygen gas is exothermic. It's going to release that energy to the surroundings. The decomposition here of mercury to oxide into mercury and oxygen is an endothermic reaction, also takes a little bit more energy to do so. As you can see in my really badly drawn here, so I'm gonna get rid of all that. We could also see, just looking at our diagram here, which one has a greater activation energy. The endothermic reaction, right? Which is why it's probably endothermic. It needs a little help to get everybody kind of up and over the hill versus obviously the guy on the left there, which actually has an excess amount of energy, if you want to think about it that way, that can release it as it's going through there. Also, the activation energy determines, again, how fast or slow that reaction takes place. A bigger activation energy, a slower reaction usually. So when we talk about exothermic and endothermic reactions, we also talk about it in terms of, is energy sort of a reactant or product? We sort of talked about that when we did Le Chatelier's principle. We talked about temperature. And typically speaking, when we think about an exothermic reaction, we think of heat and energy as a product, like it is being given off, like in the chemical reaction. And when we talk about an endothermic reaction, we think of heat and energy as being a reactant, like it's being absorbed. So here, as we talked about before, if you have some water at some different temperatures here in this isolated container, insulated container, heat is going to flow this way. When it does so, all the water molecules in here are going to gain some energy, start moving around a lot faster. The result of that is we're going to see the temperature start to rise on this side. When this side loses the energy, everybody's going to slow down a little bit, and we will start to see the temperature decrease here on the left as that transfer of energy is going. That is really what we can use temperature to measure, right? Is sort of the transfer of energy. If we see the temperature increase, then that substance obviously gains some energy to do that. If you see the temperature of something go away or lower down, then obviously that thing is releasing the energy, right? In that case. Now, again, eventually what will happen here is, you know, they'll kind of equal out there probably about halfway between their temperatures there at 50 degrees. They'll come basically to equilibrium with each other, right? In terms of their temperature, as that energy will be transferred enough that everybody will end up at the same temperature. Now, enthalpy, as I mentioned before, is really the measure of how much heat or energy is released in a chemical reaction. It probably is the most common sort of way that we express energy. And enthalpy is oftentimes calculated as the delta H. And as I mentioned before, very common way that we do this is to calculate and add up all the delta H values of our products minus the delta H value of our reactants. And again, really the number doesn't matter all that much in terms of exothermic or endothermic. What does matter is the sign. So again, if you see a negative sign for delta H, you know it's exothermic. And if you see a positive sign, you know that it is endothermic in this case. There is a table where you would look up these values known as the delta H of formation table, and you would look them up based on the substance. It's also really important when you would do so that you make sure you get the substance you're looking for, but you also make sure that you do get it in the correct state. And I say water is a very common one that people mess up on. Just find the first H2O they see in the table. It might not be the right state that you need. So you do want to make sure it's not just the substance, but whatever the state may be, as a solid, aqueous, gas, whatever it may be. So here are some values of delta H of formation from a table. So why don't you calculate that? And by the way, before we do that, let's just talk about more so maybe how to do that. That'd be good. But like there would be another slide there, but there wasn't. So for example, if we had this reaction of 2A plus B goes to 4C, and we want to calculate the delta H of this reaction. Basically, we would go to this table of our delta H of formations, and we just make up some here. So A will be 20 kilojoules, B will be -4 kilojoules, and C will be, why not, 15 kilojoules, why not? Now, when we go to calculate this, it is also important that you take into account the coefficients in the equation when you're calculating these, and it does matter in this case. So if we were to calculate this, we would do our products minus our reactants. And basically what we would do in this case is take our delta H of our reaction. We'll start on our product side. There are 4 C's. We would take 4 times the value of C, which typically this is kilojoules per mole. And we'll take 15 kilojoules there. That is all of our products, basically. This is basically moles and times moles here. We're going to then subtract it from all of our reactants. So there are 2 A's. So we do have to take 2 times the value of A we find in there, which is 20 kilojoules per mole. I'll put it in here per mole. And we then need to add it to our other reactant, which is B. And in this case, that is going to be 15 kilojoules per mole. Technically speaking, we would be multiplying this by 1, which we don't really need to do, but technically we'd be multiplying by 1, which is the coefficient here. We would add all those together and subtract. So we'll take 4 times, what did I do there? 15 minus we got 2 times 20 plus 15. I feel like I did 15 twice there. I feel like I did. And A was 20 and B was -4. That was like way, way wrong there. Hey, I'm still on spring break. Let me laugh. All right, so let's get the right number from my bad made up table there and actually put the right number in there. So that's going to be actually B, which is 1 here. So that's going to be -4 kilojoules. There we go. Let's try that there. All right. So we got -4 in this case. There you go. That's going to give me 24, I think, in this case. I hope. For my delta H of this reaction. This reaction would be exothermic or endothermic? This would be endothermic, as it is a positive value here for delta H. So you do have to take into account the coefficients. You got to multiply them by the values that you find in the table. By the way, delta H is a formation for things in their standard states are going to be 0 kilojoules, like O2, H2, N2, anything uncombined kind of by itself will have a delta H value of 0 in those tables if you look them up. All right, now let's try a real one here, maybe. That's right. There you go. All right, so those are values you find from the table. Calculate the delta H for this reaction here. Here and see. There we go. There it is. All right, so here we're going to do our products minus reactants. Obviously, if this was not provided for you, you would need to go look it up in a table, as we just talked about, find the delta H formation for these things. We're going to basically do our products minus our reactants here. So our delta H of our reactants, our reaction, will be our products. So we have 2 sodium hydroxides at minus 470 kilojoules per mole. We also have H2. So as I mentioned before, typically on these tables, anything in its standard state will be 0 kilojoules, even though we may just have one of them. That's going to take care of all of our products here. We're going to subtract our reactants. And in this case, we got what we got there, our 2 sodiums, which also should be 0. And we're going to add it to our 2 waters in the liquid state, which will be minus 286 kilojoules per mole. And that's going to get us here basically 2 times minus 470 minus basically 2 times negative 286. That's going to give us a negative 368 kilojoules as our delta H for this reaction. That will tell us it is exothermic because we do have a negative value. Any questions on that one there? All right, let's try another one here. Maybe. Why don't you try that one? Super small. I don't know. Shrunk. All right, give that a go there. Calculate delta H for this one as well. Okay, so let's take a look here. Again, we're going to do our products minus our reactants. So on our product side there, we got 16 COs. Again, from the table there, minus 110 kilojoules per mole. We will then add that to our other product, which is our water. We got 18 of those at minus 286. And again, that's going to take care of all of our products. We're going to do our reactants. So I'll just put it underneath to save a little room here. We'll go 2 times our first guy there, which is negative 208 kilojoules per mole. We will then add it to our 25 waters, which are oxygens, which are 0 kilojoules per mole. And that's going to get us here 16 times minus 110 plus 18 times minus 286. And then we're going to subtract it from essentially 2 times negative 208, it looks like. It's going to give us a negative 6492 kilojoules. Once again, here we hit a negative value. So that does tell us that it is exothermic. Any questions on how to calculate delta H here? So pretty straightforward. Again, this is the idea of state function. Again, products are final state, right? Minus our initial state, which is our reactants when we talk about a chemical reaction. And that again is, as I mentioned earlier, how a lot of thermodynamic properties are calculated from the equation products minus reactants. All right. All right, so let's talk about another sort of aspect of this. And sometimes when we do have equations or reactions that involve delta H values, we can do sort of I guess it's sort of like a stoichiometry sort of relationship, if you will. You could get some stoichiometry sort of conversion factors, your kind of mole to mole conversion factors. You also can get sort of a mole to energy conversion factor from an equation as well. So for example, here we have this combustion of propane. We could see that for every 1 mole of propane, we get out minus 22, 21 kilojoules of energy. And we could get that basically like we do a mole to mole relationship if we're just doing stoichiometry. We could use this as a conversion factor and flip it around and go minus 22 to 1 kilojoules up on top and 1 mole of propane there on the bottom. So for example, we want to know what is the delta H if we add 0.113 moles of propane is burned in this reaction. So in this case, we basically could do a stoichiometry problem that involves moles and energy. So here we'll go 0.113 moles of propane. We will choose our appropriate conversion factor, which would be this guy here on the right. We're going to go opposites so that they cancel. Moles of C3H8 on the bottom, minus 2221 kilojoules up on top. This is dimensional analysis, as you hopefully remember. That is multiplying on top and dividing on the bottom, basically. That is going to get rid of our moles. And we would have 0.113 times minus 2221. Going to get us about minus 251 kilojoules of energy would be burned in this case, and it would be released in this case as it is a exothermic process. So another very common thing is we can sometimes use an equation as a sort of thermochemistry type of conversion factor that involves energy and moles. You could do that, by the way, with anybody that's in here. You could say for every 5 moles of oxygen, you get that much energy out in this equation, 3 moles of CO2 or 4 moles of water. So you can really use it for sort of anybody in that equation. And it's very much just like a mole to mole relationship, except it's a mole to energy relationship that allows you to do that. Variations of this is obviously you would not be given that perhaps maybe in moles, but in grams, you use the molar mass converted to moles, and then you can use that relationship. So very much like your kind of opening step in a stoichiometry problem, where whatever they give you convert to moles, and then you can kind of use the equation as a conversion factor to get, in this case, to sort of the energy component of it. Questions on that there? All right, so that brings us to specific heat and specific heat capacity. And this is something that you should really get in the previous class, which I think they're going to throw it back into. But you might have talked about specific heat probably in 100. I think they might do that still in 100. But specific heat capacity is the amount of energy that's required to change 1 gram of a substance by 1 degree Celsius. And there's an equation that we use for specific heat, and that is Q is equal to ms delta T. Q is our heat, our energy, and it typically has units of either joules or calories, in this lowercase calories. M in this case is our mass, and it typically has units of grams. S is actually our specific heat capacity. So S is our specific heat capacity. And it is the one that actually has 3 units associated with it. It is either joules per gram per degree Celsius or calories per gram per degree Celsius. So those are the common units for S. And delta T here is our change in temperature. It is one of the few things in chemistry that you actually do not need to convert to Kelvin. And this is actually in degrees Celsius here. And that's because in chemistry, we typically will use a specific heat capacity that's in degrees Celsius. So everything cancels out correctly. Physics, I think they go Kelvin on that. But here we do use degrees Celsius. The more important part of delta T is how you calculate delta T. And it's really important to make sure you always do final temperature minus the initial temperature. And the reason for that is why it's important is when you calculate Q, if you end up with a negative value, that tells you it is exothermic process, heat and energy is being released. If you calculate Q and it ends up a positive value, it is endothermic. So why is the delta T really important for that aspect of it? It's because mass is a positive number, specific heat capacity is a positive number. So the only place where you could get a negative number is going to be resulting from the delta T. So sometimes people in an earlier class are taught just take the difference of the temperature, but here you don't want to do that. You do want to always take final minus initial. That way, if you get a negative number, then you will get a negative Q, which is what you're supposed to have. Or if you get a positive number, then you will have obviously a positive number for Q as well. So that's really important. Again, as we talked about a little bit ago, if it is something where it is an endothermic process, somebody is going to be gaining energy. The result of that is their temperature should increase, which means their final temperature should be larger than their initial temperature, and that will give you a positive delta T. If somebody is losing energy, their final temperature is actually going to be lower than it started because their temperature is going to go down, which means their final temperature will be smaller than the initial temperature. So when you subtract that delta T, you'll get a negative number. So again, taking final minus initial is really important for the actual correct sign that you get for Q. Will you get the same number if you just take the difference? The answer is yeah, you get the same number, but you won't have perhaps the correct number if it is a exothermic sort of process. Any questions on that? Now, I personally roll with S for specific heat capacity. Some people use C for specific heat capacity. Some older books used to use SH for specific heat capacity. So sometimes the symbol for specific heat capacity could be one of those three is typically what you see. But I personally use S, so I will use S here. But again, if you see C, that also means specific heat capacity. So sometimes books will use some different sort of symbols for it. When you calculate Q at a constant pressure situation, which is most cases what you do, for example, if you did it in lab, you are actually calculating the delta H for that reaction. You calculate change in enthalpy will be the same value for that. One of the nice things and simple things that you maybe have done before and will do again is you could basically just do this type of process using like a coffee cup and a thermometer, except if you do it here where they bought fancy things instead of just giving you a thermometer. So the lab takes a lot longer than other just sticking a thermometer in there. But in this particular case, all you need is basically the thermometer to follow the temperature change, and you can use the specific heat equation to basically figure out the change in enthalpy or how much heat is being given or taken. One important number that we use a lot is the specific heat capacity of water. This is actually liquid water, by the way. And if you wanted the specific heat capacity of steam or ice, which is also water in different phases, it's more like 2 rather than 4. So you do want to make sure you find it in the correct phase. 4.184 joules per gram per degree Celsius is the specific heat capacity for liquid water, or 1 calorie per gram per degree Celsius. The higher the specific heat capacity, the more energy you need to put in there, right, to change the temperature by 1 degree Celsius, which means the more energy you need to put in there to see a big temperature change, right? It's also related to how many grams that you have as well. So that's what we were talking about a little bit earlier. You have a cup of coffee, not as much water there, so not going to take as much energy to see a bigger temperature change because you don't have as much water as opposed to the bathtub where you have a lot more water molecules, so it takes a lot more energy to see a temperature change. Specific heat capacity of liquid water is relatively high. That is why people get a little concerned when the ocean water, right, changes by like 1.1 degree or something like that. But if you think about how much water is in there and how much energy is needed just to move it that little bit, that's a lot of energy and stuff like that. Here's a table of specific heat capacities, and as I mentioned before, as you can see here, ice is actually 2.03 and gas or steam is 2. Here we have aluminum 0.89, silver, and so forth. So these again are specific heat capacities that you may have to look up in a table to do some problems. So once you want to go here, determine the amount of energy as heat that is required to raise the temperature of 10 grams of aluminum, specific heat capacity 0.89 from 25 to 58 degrees Celsius. Give the Okay, let's take a look. So we want to determine the amount of energy. So that is Q. We obviously have the mass given to us, which is 10 grams. We have the specific heat capacity, 0.89 joules per gram per degree Celsius. We have our initial temperature here, 25 degrees, and our final temperature, 58 degrees. So going into our equation here, Q is equal to ms delta T, our mass of 10 grams, our specific heat capacity of 0.89 joules per gram per degree Celsius. Again, final temperature, which is 58, minus our initial temperature, which is 25. And that's going to get us here about 293.7 joules, as the grams will cancel, the degrees Celsius will cancel, and maybe something like 290-ish on a significant figure, remembering type of situation in this case. This is a endothermic sort of process, as we got a positive value for Q. And we also see that reflected in the temperature. Temperature went from 25 to 58, so it picked up energy. The result of that is our temperature increased. Question there. All right, let's try one more here. 294 joules of heat is transferred to 10 grams of silver. What is the final temperature here? The specific heat capacity of silver is 0.24 joules per gram per degree Celsius. Oh, I didn't do calories today. I'm sorry. I should actually read the question off. So we do on the calories. So there are 4.184 joules in a calorie. So I'll take the rounded number there, 290 joules. Again, 4.184 joules per calorie. So we'll go 290 divided by 4.184 and give us about 69 calories. If you took sort of the non-rounded number, you'd get something similar. You get like 70 calories. Pretty close if you took on. Thank you. Okay, so let's take a look. We got our Q, which is 294 joules. Again, we have our mass, which is 10 grams. We have our initial temperature here, which is 25 degrees Celsius. We're looking for a final temperature, and we do have our specific heat capacity, which is 0.24 joules per gram per degree Celsius. So again, try not to get these two confused. It's a very common error. People kind of always swap them out for the wrong side. We really could go into our equation here. Q is equal to ms delta T. And in this case, I'm going to actually just solve for delta T. Delta T would equal Q divided by ms. Again, just dividing that to the other side to do so. That will give me delta T is equal to my Q, which is 294 joules, divided by my mass, which is 10 grams, and my specific heat capacity, 0.24 joules per gram per degree Celsius. Here, the joules will cancel, the grams will cancel. When I divide that delta degrees Celsius will come to the top. 294 divided by 10 divided by 0.24. It's going to give me a change in temperature of 122.5 degrees Celsius. A reminder, though, that that is not the answer. That is just the actual change in temperature. We're looking for the final temperature here. So again, this is where the change in temperature, final minus initial, is important. That means that we got like 122.5 degrees Celsius equals our final temperature minus our initial, which was 25. This is also important because I need to add that to the other side and not subtract. So we'll add 25. It's going to give us about 147.5 degrees Celsius at this point, which is our final temperature. And I would probably not round at this point. I would, if you wanted to round to the proper number of digits, which might be 2 in this case. You might want to round in this case to that. There. All
or take that number, around that number instead of rounding earlier. Questions on that there? All right, we will lay it up there, I think, for today.